I wanted to make this video. This is my lecture for tomorrow on Monday, the day before the AP exam, and I wanted to make sure that if anybody missed school or missed the class because they were taking another AP exam, that they would have what we did in class. So here you go. Last time we discussed how to tell if a function was even or odd. We said that even functions are determined that f of negative x gives you exactly the original function back. And we said that odd functions, the test was if f of negative x gives you the opposite of the original function. And we showed examples of what that meant. Okay, some examples of even functions. We looked at the absolute value function, x to an even power, the cosine of x were all examples. All of them have the property that they're symmetric about the y-axis when you graph them. This looks a lot like x squared. And if AB is on the graph of an even function, so is the opposite of AB, negative AB. There's a benefit to that when you're doing integrals, and that is that the integral from negative a to a, from all the way to the left side to the right, is just twice what you get from 0 to a. 0 is always a nice number to plug into problems, so you may save yourself some work if you recognize that symmetry, and you can change a problem that looks like this into a problem that looks like that. Okay, on the odd side, some examples of odds were x to an odd power, or the sine of x. They're symmetric about 0, 0, the origin. If AB is on the graph of an odd, so is negative a, negative b. And what that really means, symmetry about the origin, is if you connect AB with negative AB with the segment, the origin will be the midpoint of that segment. There's also a real nice benefit when you're doing integrals in that the integral from negative a to positive a for any odd function f of x is always 0. That's because there's just as much area below the x-axis right there as there is above the x-axis over here. We're going to spend a lot of time today looking at 3 different definitions of the derivative. 2 of them we already really know. We've worked with this guy for a long time. Adjust my camera. Okay, we've worked with that guy for a long time. And the basic idea here, well, this is what we memorize. It's the limit h approaches 0, f of x plus h minus f of x over h. It's the limit of a slope, where we're connecting a point f of x, f of x, to another point that's h units to the right. So it's x plus h, f of x plus h. And initially, you're looking at a segment connecting those two, and you're getting their slope, y2 minus y1 over x2 minus x1, which when you simplify it just turns into what you see there, but after the limit. Then, that clearly is not the same slope that you get down here, and that's what we're trying to compute when we compute a derivative. So we let h become close to 0. As h gets close to 0, that expression gets close to x, and the points get infinitely close together, and we end up with a formula for the slope down here. Okay, the important thing about this one, that f prime of x is a function of x. You're going to get an answer typically that has x's in it. The derivative of x cubed is 3x squared. The derivative of sine x is cos x. Okay, so our first example of that one, I have the book and I'm on page 98. And I'll adjust the screen back up again. Okay, here we're finding the slopes of the tangent lines to the graph x squared plus 1. What they're really finding is a formula. You see their answer, they're using c's instead of x's, but their answer is 2c. This is really a formal definition of the derivative proof for the function x squared plus 1. They're finding f prime of x. What I've done to emphasize that, and this is page 4 amongst all the pages you have. I'm not sure why it got down there. That's the reason I didn't give it to you stapled. So this is your page 4. This is the same page, and all I've done is I've changed the x's the c's that they had into x's. So for that function, we are finding f prime of x, the derivative function. So f prime of x is the limit delta x goes to 0. Remember, the book uses delta x instead of h. F of x plus delta x minus f of x over delta x. Well, f of x plus delta x is what you get when you stick an x plus delta x right into that guy. So it's x plus delta x squared and then plus 1. So there's your x plus delta x squared plus 1 minus f of x, which is just the function x squared plus 1. Be careful when you do your squaring on a problem like this. That's essentially multiply x plus delta x times x plus delta x. Remember, you get a middle term. So this is x squared plus 2x, that's an x there, delta x plus delta x squared, and then the plus 1 is right there. Remember to distribute your minus across those two, and you've got that. Well, you're going to get some cancellations, which gets you 2x delta x plus delta x squared over delta x. And since all three of these terms have a delta x in them, we can get rid of 1 power of delta x from each. And now we can take our limit. We couldn't plug in 0 for delta x before because we always had a delta x in the denominator. But now we can, and our answer is 2x. That means our derivative equation is 2x. So our slope could be determined by plugging a value for x in there. For instance, at -1, 2 times -1 will give you a slope of -2. But this is a formal definition of the derivative proof where we found f prime of x. Now sometimes what we really do want to find is just the derivative's value at a single point. Well, you can use the original definition of the derivative to find the derivative at a single point. That's when they were using the c f of c thing, but they used it and left the c's in, whereas when we use it, we're going to actually have numbers there. F prime of 5 will be f of 5 plus h minus f of 5 over h, limit h goes to 0. Here's the picture. So now it's at the point c f of c, we want the derivative. So it's y2 minus y1 over x2 minus x1, and you're doing the limit h goes to 0. The difference in this one is up top, f prime was in function. Down here, f prime is just a single number, which is the slope of the tangent to the graph at x equals c. So I've done that for the same problem that we just looked at. F of x is x squared plus 1, and we're going to find f prime of -1 using our formal definition at a point as opposed to formal definition overall for x. It's the same definition. So here we go. F prime of -1 is the limit h approaches 0. Instead of f of x plus h, it's -1 plus h. Instead of f of x, it's f of -1. That's the only difference. You'll be working with a lot more numbers. We've done this, so this is not really new. This is the limit h goes to 0. -1 plus h squared plus 1. Remember, it was x squared plus 1, and my x in this case, if you will, is -1 plus h. Plus 1 minus f of -1, which would be by the formula -1 squared plus 1. Okay, when I evaluate that, that just gives me plain old 2. And when I square this out like we did in the other one, I get this. This time, some of the constants go away, and again, you're left with an expression that has h's in 3 spots, just like we had delta x's in 3 spots. 1 power of h cancels out of each, and now I'm here. Now I can plug the 0 in, and I get -2 for the answer. So again, this is really just using our original formal definition of the derivative, but instead of having x's in a lot of spots, we have numbers where those x's were. Okay, there is an alternate definition of the derivative. This is it. And I'm going to find that paper. Found it. So here is our alternate definition of the derivative. It's the same idea. It's just a renaming of the points. Here we've got the point c f of c and the point x f of x. We want the derivative, the number that is the slope of the tangent line at c. Again, in this version, your answer will be a number. It will not be a function. So what's the slope? Well, it's f of, between these 2 points, it's f of x minus f of c over x minus c. exactly what you see there. And what we're going to do to find the slope at c is we're going to let this x slide down the curve so it's the limit as x approaches c, f of x minus f of c over x minus c. To me, this is an easy definition to remember. Notice that you've always got x first, c second, so it's the limit x goes to c. It's f of x minus f of c, and it's x minus c. Okay, so I'm going to show you how to use that definition of the derivative, again, to find the same thing we did last time. So here we go. I'm using the alternate definition of the derivative, which is there, to find f prime of negative 1. Again, this is the same function we used before. X squared plus 1 is my function. Okay. Maybe. Okay. So, I'm just going to write over in the somewhere here that our function, so we can remember, f of x is x squared plus 1, just so it's easier to point to. Okay, so here we go. F prime of negative 1 says it's the limit x approaches that number, negative 1. F of x, that's easy, it's x squared plus 1, minus f of, well, that's the number that's here, f of negative 1. If I said 1 before, it was negative 1. So that's negative 1 squared plus 1, like it was before. Then x minus a negative 1 in the denominator. Okay, well, here that gives us x squared plus 1. This is minus 2 over x plus 1. 1 minus 2 would be negative 1. So now we have x squared minus 1 over x plus 1. Well, that's the difference of squares. We can factor that. And the x plus 1's cancel. And looky, looky. This is the limit x approaches negative 1 of x minus 1. We can plug in the minus 1. We get minus 1, which is minus 2, which is exactly what we got in our other case. So there's one example of using the alternate definition of the derivative. Okay, you might remember this example. Here we're finding for the function, this is f of x equals the square. This is f of x equals the square root of x. We're finding f prime of x by the limit definition of the derivative. And you might remember that this is the one that you had to multiply by the conjugate. And it got kind of messy, but eventually you could cancel out some x's, and you ended up way down here. It was 1 over 2 root x. Okay, so that is using the formal definition of the derivative. If you were doing that same one using, notice the formal definition of the derivative at any x, which is a function, and the formal definition at c are the same definition. The x's just turn into c's. Okay, so you can almost not even use that one. You can just know that if you have a number stuck up here, you're going to get a number for an answer. Okay, but formally, it's that guy. Okay, so I just wanted to point out that if you were doing f prime of 5, for instance, instead of f prime of x, all that would happen is that every x that you see, except for the one next to the delta symbol, every x is going to change into a 5. And you're going to end up with 1 over 2 root 5 for your answer. Now, I want to show you how the alternate definition makes this a little easier problem for f prime of 5. There's nothing we can do about f prime of x. It's going to be a little bit of a bear no matter what. But again, we're going to find f prime of 5, which we know is 1 over 2 root 5, for f of x equals the square root x, using the alternate definition of the derivative, which you see right there. So, f prime of 5 is the limit x approaches 5, f of x, the square root of x, minus f of 5, which would be the square root of 5, over x minus 5. So you multiply by the conjugate like you did before. And when you multiply the tops, you get, it's another a minus b, a plus b. The roots go away. You're to here. And now this immediately cancels. And now you just have the limit x goes to 5, 1 over root x plus 5. You plug in the 5, 1 over root 5 plus root 5 is 1 over 2 square root 5. So here's a case where I think for a derivative at a single point, the alternate definition turns out to be a pretty good deal. Okay, I want to make a real quick point about something called the greatest integer function. I don't know that it's ever going to appear anywhere, but it's this guy at the top of page 102. What is it's called the greatest integer less than or equal to x. Okay, and what happens is that each integer, it jumps up. The greatest integer less than or equal to -2 is -2 until you get to this point. At -1, it jumps up to -1. Then the greatest integer less than or equal to -1 is -1 until you hit 0, and then it's 0. The greatest integer less than or equal to 0 is 0 until you hit 1, and then it jumps up there. The greatest integer less than or equal to, like all the numbers in here, 1.2, 1.3, is 1 until you hit, right here, you hit x equals 2, and then it jumps up. So it just jumps up by 1 at every whole integer. I bring that up just in case it ever comes up somewhere. I don't think it will. It's typically used as an example of a function that has jump discontinuities. That's its main purpose. Okay, what I wanted to talk about on this page is this guy. Again, we looked at the absolute value of plain old x last time. We didn't really get to talk. We talked about what the derivative was on the left branch, which we saw was -1. We did a definition of derivative proof where we knew that we were on that particular branch. That was of the original absolute x graph. You can look at your notes from Friday. Unfortunately, it was one day this year everybody was there. Okay, so what they're doing here, I just wanted to explain, if we attempt to read through what they're trying to show. They're trying to show that this function is not differentiable at x equals 2. We can see it because we see the graph and it has a sharp point. But how could you do a limit proof with a formal definition, in this case the alternate definition of the derivative? How could you use that to show a lack of differentiability? And what we're going to show is that we know that when left-hand limits, that's the limit x approaches 2 from the left, and right-hand limits are different, we know the overall limit fails to exist. So, again, we're using this alternate definition of the derivative right here on the absolute value of x minus 2. Okay, well, in the book, they do a reasonably good job of getting started. They show you that this would be for where the limit as x approaches 2, they're doing the limit as x approaches 2 here to find the derivative at 2. So this is the limit x approaches c, f of x minus f of c over x minus c. This is the one-sided limit derivative, if you will. Okay, so what is f of x? Well, it's the absolute value of x minus 2. What is f of 2? It's the absolute value of 2 minus 2, which is 0. What they don't tell us is how did they get to here? And they got to here by knowing that if you're approaching 2 from the left-hand side, then the absolute, you'd be doing like the absolute value of 1 minus 2, and that's negative. So as x approaches 2 from the left, x minus 2 is less than 0. That means that the absolute value of x minus 2 equals its opposite. It's the opposite of x minus 2. And that's not showing up. I thought I could save some stuff, but I've got that written here. Thought I'd save going to there, but let's just go to there. So what do we have? Same thing we've got up here. Absolute value of x minus 2, and that's the 0, the 2 minus 2. So our argument is, as x approaches 2 from the left side, x minus 2 must be less than 0, so its absolute value is its opposite. So that's already been 0, so it's gone. With absolute x minus 2 gets replaced by the opposite of x minus 2, and this then becomes, they cancel there, and we get -1 for our answer. On the right side, it's the same kind of deal. The limit x approaches 2 from the right, and this is f prime. What we're doing in both cases is we're finding f prime at 2, but from the two different sides, by the alternate definition of the derivative. So on this one, this would be absolute x minus 2, that's our f of x, minus f of 2, again, is 0, over x minus 2. The reason that that turns into 1, again, is the definition of absolute value. And again, remember from last Friday, that's the definition of absolute value. Absolute value for positive things are themselves when things are bigger than 0, but it's their opposite when they're less than 0. Like the absolute value of 5 is 5 because 5 is bigger than 0. The absolute value of -5 is the opposite of -5, which is also 5 because -5 was less than 0. Okay, in this case, on the x approaching 2 from the right, again, this is a one-sided derivative. This is f prime of 2 from the right side. So notice right here, f of x, that's your absolute x minus 2. F of 0, f of 2, rather, is 2 minus 2 is 0. So our question is, how do you get rid of the absolute values? Well, you do it by the definition of absolute value, that you just say, as x is going to 2 from the right side, you've got numbers bigger than 2, like 3. 3 minus 2 is positive, so the absolute value of x minus 2 in this case is just itself. So that gets replaced with x minus 2. That was 0, so you get x minus 2 over x minus 2, which is 1. Okay. The point being on this one that the one-sided limits are different, okay? And therefore, this function is not differentiable at 2. It is a sharp point when the one-sided derivatives are different values. Now, we are about done talking about the definition of derivative problems. I have a problem here. You might wonder, on this graph, we've done these one-sided derivatives, but how would I deal with absolute value if they ask me to find f prime of 1? Okay, that's 1 right there. And we know it's going to be -1 because that's the slope on that side. So I've done that two different ways in the file here. So here is the formal definition of the derivative proof, sort of completing different types of proofs that we know for formal definitions. If I can get that just right. Okay, so what we're doing is, what if the question was, for f of x equals x minus 2, what's f prime of 1 using the definition of the derivative? And again, this will be the definition of the derivative at a point, because we're given a point. So using our first version of the definition of the derivative, which is essentially this guy, written for a point, so f prime of c, and we're going to be plugging a 1 in for these guys. That's the definition we're using. Okay, so f prime of 1 is the limit h goes to 0, f of 1 plus h minus f of 1 over h. F of 1 plus h is what you get when you replace that x with the 1 plus h, so you get 1 plus h minus 2 minus f of 1, which would be absolute value, 1 minus 2. Okay, then as you're looking at this guy, you know the absolute value of -1 is 1, so that's going to get filled in right there. So it's the minus is from the fact you're subtracting -1, and you just make the argument that as h approaches 0, this is getting close to -1, so it's got to be negative. So you can replace that. You can replace the absolute value of -1 plus h with its opposite. So -1 plus h is turned into the opposite of -1 plus h. When you do your subtractions and things clear, you end up way down here, and you get the limit h goes to 0 of negative h over h, which is the limit h goes to 0 of -1, and that's a constant, so the answer is -1, exactly what we knew the slope on that graph was going to be. You can do the same one by that same problem by the alternate definition. In that case, by the alternate definition, again, that's that guy right there, you've got f prime of 1 is the limit x approaches 1, f of x minus f of 1 over x minus 1. Remember, our f of x was absolute x minus 2. And then minus f of 1 would be absolute 1 minus 2. That gets us to here. And again, we use the argument that, well, we know absolute -1 is -1. Okay. We use the argument that as x approaches 1, this is getting close to 1 minus 2, which is -1, so it's less than 0. So its absolute value is its opposite. So you replace absolute x minus 2 with its opposite. You distribute the minuses, and finally you will get down to here in a couple steps. Now, this looks like it's not going to work, but if you factor -1 out of the top, now you've got this, your x minus 1's cancel, and this is the limit x approaches 1 of -1, which is -1. The same answer that we got there, and the same answer we knew we had to get because the slope over there was always -1. Another problem that doesn't appear on one of the book pages, but we've done, is this problem where you're finding f prime of x when you've got this fraction here. I wanted to remind you about that guy. If you're doing this as a formal definition of the proof where you're finding the formula, you're finding f prime of x as a formula, remember the key on that guy is once you get here by saying what is f of x plus h, remember f of x plus h is what I get when I plug in x plus h right there. All right, so I'm going to plug in x plus h right there. I get 4 over x plus h minus f of x, 4 over x over h. The idea was you're going to get a common denominator, which will be always these two multiplied together. So my common denominator is those two multiplied together. To make that denominator happen on this side, you have to multiply top and bottom by 4. That's why over here you've got a 4x. The minus sign comes from the minus sign there. Okay? And let's see. Then this is minus 4 over x. That's minus f of x, the function. Okay. Let's see. I think I've already gone through that. I've done this video twice now, so I'm forgetting where I'm at. Oh, I had to multiply top and bottom here by x plus h. That was my point. That's why an x plus h appears there. Okay, and I wrote the bottom as h over 1 because I'm going to flip it over and multiply. I get to here. Some good things eventually happen. Eventually, you're going to be able to cancel your h's, and you're going to get way down to here. You can put a 0 in for that h now, and you get -4 over x squared. Okay, if you were doing this,
Mary?
Hold on, honey, I'm in the middle of video.
Oh, sorry.
Okay. All right, now I've got the same one, and I'm finding f prime of 2. Nothing much changes in this version, and I'm using this definition of the derivative here. It's the original formal definition of the derivative, but at a point instead of for a function answer. And the only difference is now I've got, instead of f of x plus h, I've got f of 2 plus h minus, instead of f of x, f of 2. It works out a little bit simpler this time because most of us like working with numbers. Okay, so f of 2 plus h is what you get when you put a 2 plus h into your function. And remember, our function was f of x equals 4 over x. So if that's our function, f of x plus h is 4 over x plus h. I'm sorry, I'm not doing x plus h. I'm doing 2 plus h. So f of 2 plus h is 4 over 2 plus h, which you see right there, minus f of 2, which would be 4 over 2. You got to maybe resist the temptation just to make that a 2 because you want to play the same common denominator game. So here I'm doing that, and the common denominator is those two multiplied together. So this numerator, because I need to multiply by 2, because 2 times 4 is 8. okay? And then you get minus, I've got to multiply this side by 2 plus h. So I get that 4 times 2 plus h, which distributes to minus 8 minus 4h. I'm going to take the denominator like I did before, and I'm going to make that h over 1, flip them over and multiply. That gets me here. You can't read this. This is an h right there. Okay, which last time I made h over 1, so there will be consistent. Okay, this is going to come down to here, and now I can cancel my h's, and I can plug my 0 in, and I get -1 for the answer. Finally, here's that same proof done with our new guy, the alternate definition of the derivative. F prime of 2, and again, what am I talking about? I'm talking about that definition right there. And the function, again, is 4 over x. So, I'm doing f prime of 2 is the limit x goes to 2, f of x minus f of 2 over x minus 2. That's the limit x approaches 2. Again, the function was 4 over x, so that's 4 over x minus 4 over 2 over x minus 2. You still play the same common denominator game. You multiply top and bottom there by 2 and top and bottom there by x to get this. That takes you down to here. I took that denominator here, there, put it over 1, and I flipped it over. Now you just play a little factoring game. You factor a minus 4 out of the top. That gets you there. You cancel. And you get -4 over 2x as x goes to 2. That's -4 over 2 times 2. You've got -1. This is a really long video. Okay, we're done talking about formal definition of derivative in any form, sort of. Yay. Except that we're not. What we're saying now, we're not asking you to do formal definitions, but we're saying, how might those formal definitions appear in other problems, like amongst limit problems? And we've seen this problem before, I think, or one like it on one of our AP or IU exams that we've looked at. They want you to do the limit h goes to 0 of something that looks like that. Well, what you have to realize is that's a derivative sitting there. For our regular definition of the derivative at a point, c, instead of x, what we have is, this is f prime. This is f prime of the sine function, which is the cosine function, evaluated at pi over 3. And so we get that our answer is, knowing that the derivative of sine is cosine, I'm going to evaluate that at pi over 3, and the cosine of pi over 3 is 1/2. Here I use my little special triangle. Adjacent over hypotenuse gave me 1/2. Now, you might also see this as an alternate definition problem. That's the main reason I took you through all those alternate definitions today. You don't really have to use the alternate definition very often. You just need to know that it exists and it's an option, and we saw it made at least one problem easier. But what you need to know is if you recognize that definition, that's about all you need to do. Here it sits. If amongst a bunch of limits you saw the limit x approaches pi over 3, sine x minus sine of pi over 3 over x minus pi over 3, that's exactly this is exactly this f prime of c, where the function is sine x and you're doing pi over 3. And so the answer, again, is the derivative of sine x evaluated at pi over 3. Your answer comes out exactly the same as before. I wanted to make a comment about how can you tell from a formula whether you're at a sharp point or a vertical tangent, and it depends upon the derivative. So I'm going to show you a sharp point, and this is way after talking definition of derivative stuff. This is, I know how to take derivative in all the ways I need to know how to take it. So if you look right here, here's f of x is x to the 2/3. We know by our normal derivative rules that you would have f prime of x equals that, bring the power out front 2/3, lower it by 1, it's this. And if you can't read, that's a 1 there, 1/3. Okay, we know we have a critical number at 0. And we know the original function was defined there, so it's not an asymptote. Okay, now we're going to take the limit of our derivative function as we approach 0 from each side. If you approach 0 from the left, you're approaching with negative numbers, and you're doing the 1/3 power. So this is something extremely small, infinitely small negative. Your answer is negative infinity. On the other hand, you're doing the limit as x approaches 0 from the right. What's going to happen there? Well, same idea, but you're approaching with positive numbers. The cube root of a positive is positive. These are infinitely small positive numbers, and the answer is positive infinity. Because those are different, those are sharp points. That's just like the vertical tangent problem, just like the this guy here where you've got the sharp turn in the graph. I keep calling them sharp points, but AP calls them sharp turns. Point being, that's an example. This is an example just like the absolute value graph, but from a function, how I know it's a sharp turn. Sharp turn, yeah. Okay, sharp turn, not sharp point. Okay, vertical tangent. How do I know that occurs? Same process. Here's x to the 1/3. I've taken the derivative. It's that. Now, I've got a critical number. It's not an asymptote because the function's well defined there. So, I've got that f prime of 0 is not defined. That's why it's a critical number. But if I take my limit from each side, and that's the negative limit and the positive limit, what I get this time, both times, is infinity. Because there's a squared there, whether I come in negative or positive, I'm going to have 1 over something infinitely small. That's going to be big, and it's going to be positive. I get positive infinity in both cases, which means the overall limit is infinity. By the way, you'd say the overall limit doesn't exist because they're different there. And so, when that happens, when you get the same version of infinity on both, it's a vertical tangent. If they had all been negatives, if all the limits, all three of those were negative infinity, that's still a vertical tangent. Last point, vertical asymptotes. And that is, we know that when we see something like this, that if the numerator is not 0 and the denominator is, this is of an original function, not a derivative, then you've got x equals c as a vertical asymptote. Okay? And you also know that when you have a vertical asymptote at c, that means if you were doing the limit as you approach c from either side, you would get either positive or negative infinity. I just wanted you to know that process also works backwards. That if those limits are true, you would know without any other analysis that there's a vertical asymptote there. And then here's an example. Here's 1 over x. As you approach 0 from the right, you've got infinity because it's 1 over infinitely small is big. As you approach 0 from the left, you've got negative infinity. Okay? So that says that because you've got infinity, and we're not talking the vertical tangent things we were a second ago, those were just to be sure that we know what we're talking about. On the last page, we were taking limits on the derivative functions, not on to find vertical tangents. Okay, on this page, we're back on the original function, and we're just pointing out that when you have infinite limit from the left or the right, that's going to mean you have a vertical asymptote. That the process just works backwards. This isn't new information. It's just our old information expressed a different way. Okay, hope this was okay. I know it got really long. Thanks for listening.